Okay, so the first thing I want to mention are a couple results from additive combinatorics. So the first is Roth's theorem on three-term arithmetic progressions, which just says that if delta is some positive number and a is a subset of the first n numbers, and we assume that the size of a is bigger than delta times n, then as long as n is sufficiently large, then a has to contain a three-term arithmetic progression. So that's three elements of the form x, x plus y, and x plus 2y. So a variant on Roth's theorem due to Green is that if you take, again, you fix delta to be some positive number, and then you take a to be a subset of the primes less than or equal to n, then as long as a has positive relative density in the primes, then you can find a three-term arithmetic progression in the primes. And the main reason that I wanted to mention this result is we're going to use quite a few ideas from this paper of Ben Green's. But before that, so we first need to define what a sum set is. So a sum set, if you have a set A, which is a subset, say, of Z mod NZ, then the sum set A plus A is the set of things, or set of elements A plus A prime, where both A and A prime are in A. So in some joint work with Isabella Laba, we've proved the following results. So actually, we were doing some work on some results that were known in sets of positive upper density, and we looked at what happens when you look at sets of random density. So here we are sets which are random, so we don't require positive upper density, but we have an additional assumption on the set W. So if we take W to be a random subset of Z mod NZ, and then so we define W with some probability P, and then if you take A to be any subset you want of that set W, as long as the size of A is bigger than or equal to delta times the size of W, then you can show that the size of A plus A is bigger than or equal to alpha times n for any alpha less than delta. And this holds with probability approaching 1 as n goes to infinity. So here we take A to be a subset of W, which has positive relative density, and then we show that we can get positive density in Z mod NZ. Okay, so then the question is, can we prove an analog of this for subsets of the primes? So I'm going to start with an example which will show that we can't do quite as good as what we saw in the random case. So we take M to be the product of small primes, and then we define the set B to be the set of primes in Pn. So Pn here is just the primes less than or equal to n, so that P is congruent to 1 modulo M. So then the prime number theorem for arithmetic progressions tells us that the size of B is going to be 1 over phi of m times n over log n plus an error term. And if we take n sufficiently large, then we have that the size of B is 1 over 2 phi of m times n over log n. So then we take delta to be 1 over 2 phi of m. So we have a subset of the primes with positive relative density. But we can check that if you look at the set B plus B, then that's going to be contained in the set of elements which are congruent to 2 modulo m. And so we know that the size of B plus B is going to be bounded by some constant times n over m. And then using some number theoretic estimates of Mertens, this tells us that the size of B plus B is just about delta times n over log 1 over delta. Okay, so right away we have this log 1 over delta term, which didn't appear in the random setting. Okay, so how well can Karsten and I do? Well, what we're able to prove is that if you take a positive number delta, and you take A to be a subset of the primes less than or equal to n, so that A has positive relative density delta inside the primes, then assuming that n is sufficiently large, we have that the size of A plus A is bigger than or equal to a constant times delta times n, and then we have this exponential term, e to the minus c2 square root log 1 over delta. Okay, so this isn't as good as log 1 over delta. And c1 and c2 are absolute constants. Okay, so for the rest of this talk, I'm going to use f hat of c to denote the Fourier transform, which is just normalized by 1 over n. And then if we have two functions, f and g, we define the convolution f star g to be the sum over y of f of y g of x minus y. And finally, we have the LP norm. Okay, and then I'm actually going to talk about how the proof goes in the random setting, because I think it illustrates well what happens in the case of the primes, but there's a lot less notation. So, and then I'm going to talk, and then later I'll talk about how we adapt this argument to the case of the primes. So really what's important, remember we had W is a random subset of Z mod NZ, And the important properties of W is that, well, the size of W is going to be just about n to the 1 minus theta. We require theta to be sufficiently close to 0. And we have this nice bound on the Fourier transform of the characteristic function of the set W. So then remember, we took A to be a subset of W, which had positive relative density. So then we define a function f, which is just this weighted characteristic function of the set A. And we notice that if we look at the average value of f, then we actually get delta, which was the positive relative density. Okay, so then to show that the size of A plus A is bigger than alpha times n, so alpha here is any number less than delta. So you can think about this as delta minus epsilon for every epsilon or something like this. To show this, we actually want to show, what we do is we show that the size of the set of x's in Z mod nz, for which the convolution f star f is positive, is bigger than or equal to alpha times n. So there's two of the ingredients that go into this. First, an estimate of tau and vu, which is a restriction, can be thought of as a restriction estimate, says that you have nice control of the LQ norm of the Fourier transform of f for some q between 2 and 3. And then based on using this estimate, we have this decomposition of green and tau, which decomposes f into two pieces. So the first piece is bounded, and then the second piece is random in a Fourier analytic sense. Okay, so specifically this decomposition is as follows. So we take lambda to be the set of C's for which the Fourier transform is large, and then we define a Bohr set B to be the set of x's so that we have this nice approximation, 1 minus e to the minus 2 pi I xc over n is less than or equal to epsilon for every c in the set lambda. So B depends both on epsilon and lambda. And then F1 is, we average over translates of this Bohr set, so F1 of x is 1 over the size of B squared times the sum over y1 and y2 in B of f of x plus y1 minus y2. So, and then once we have F1, then F2 is just everything that's left over. So you can show that the decomposition satisfies the following properties. The first thing is that F1 is bounded. The second thing is that if you look at the average value of F1, it's delta. And this is good because you can, when you have a function which is bounded and a large average value, you can prove results that hold for sets of positive upper density. And then we have an L infinity control of the Fourier transform of F2. And we also have that both F1 hat and F2 hat are bounded by the Fourier transform of F itself. Okay, so then remember what we wanted to show was that the size of the set of x's for which f star f is positive is bigger than or equal to alpha times n. So here I'm just rewriting this as delta minus 10 sigma. So sigma is a parameter you don't have to worry about too much. And with this decomposition, we have a main term which you can prove fairly directly using that F1 is bounded and the average value of f is large. And then the error terms, for the error terms, what we actually do is we look at the L2 norm of fi star f2. So here we'll have three error terms, I guess. And then using Holder's inequality and Fourier inversion, you can show that this L2 norm is bounded by n cubed times these other norms, and each of these other pieces is bounded by the conclusion of the decomposition that we used. Okay, so how much time do I have left? Okay, so, but what happens in the primes? So for the primes, what we do is we take M to be the product of small primes. So this is what Green and Tau refer to as the W trick. So W is bounded by log n. And it depends on delta, which was fixed at the beginning. And then we partition A into residue classes, modulo M. So we say that A to the B is the set of A's in A, which are congruent to B modulo M. And then in each of these residue classes has a density inside the primes, which are congruent to that B in that residue class. So we say that delta B is the size of the set AB over PB. So P is just the primes less than N. Pn to the B is the set of primes less than or equal to n, which are congruent to B modulo M. And then if we have delta B bigger than delta over 2, then we say that this is a good residue class, and we're going to look at some sets of these good residue classes. Okay, so the next thing that we have to do is embed the primes in Z mod NZ. So n is going to be just about n over m. And if we take any element in AB, then it's going to be of the form xm plus b, and we map that element to the element x. Okay, so x will then be less than or equal to capital N. So now the notation is getting kind of bad. There's too many superscripts and subscripts. But so the first, on the left-hand side there, a to the b plus a to the b, or a to the b1 plus a to the b2. So basically, I'm considering a as a subset of primes less than or equal to little n. And then you look in the residue classes b1 and b2, and you want to see how large that subset is. And so then we map down to Z mod NZ. And on the right-hand side, we're going to bound this quantity from below. Okay, and then lastly, what we have to, so then to show that, to show the quantity on the right-hand side is large, we're going to use pseudo-randomness. And then the final step is to sum over all pairs bi and bj to get a lower bound on the original set A plus A. But the problem is that we could have two different pairs, say b1 plus b2 is equal to x, and b3 plus b4 is equal to x. So we could have some multiplicity problems. So actually this is really oversimplified here, what I've written, and it actually took us quite a while to figure this part of the argument out, and I should say that we're both very grateful to Ernie Krute for helping us with that. Okay, so in the last couple minutes, I just want to mention how we show that the sum set of a n b1 plus a n b2 is large. So Green has this modified von Mangelt function, which is defined to be phi of m over m times n times the log of mx plus b if x is less than capital N and mx plus b is prime, and it's 0 otherwise. So, and then he defines functions f and nu. So f you can think about just like rf in the random case. So it's a weighted version of the characteristic function of the set A. And then nu b is what replaces w. So nu b is a pseudo-random function in this, and we have this similar Fourier analytic bounds on nu b that we had on the original, that we had on the characteristic function of w. Okay, and then finally there's a discrete majorant property of Green, which allows us to have good control on the S norm of the Fourier transform of f. And we say that, and he shows that it's bounded by some constant which depends on S. So here S is a number bigger than 2. And what's important here is that this constant doesn't depend on capital N. Okay, so then now that we have these functions f and nu, we're able to use the decomposition that I mentioned in the random case in order to show that the size of the set of x's for which fb1 star fb2 of x is bigger than 0 is bounded below. This time we have to add, we have to look at the average value of the delta b's in each of the residue classes we're in. And then somehow we have to go back up, and that's sort of what I alluded to earlier, but I think I will stop there. Thank you.